So let's actually put this to work and learn derivatives for some new functions. Well, hey, wait a minute. You told me I'm not taking derivatives of functions today. Let's have y equals the arc sine of x. So this is a function that we've probably seen before in trig. I'd like to be able to differentiate the arc sine function. Here we've written it as y equals sine inverse of x. The exponent -1 here means function inverse, not division. I'm not such a huge fan on it, but that's the way the textbook is written. What this means, if y is equal to the sine inverse of x, well, then the sine of y is going to equal x. So long as y is subject to this condition, y must be between minus pi on 2 and positive pi on 2. Right? So this equation here, y equals sine inverse of x, and this equation here, sine of y equals x, with a condition on it, those give us the very same graphs. No, really, they do. Let's take a look at this. So let me return to Desmos. Here, we're going to graph y equals arcsine. There it is in a very lovely purple. Here, I'm going to graph sine of y equals x in black. Well, okay, that's a sine function, all right. It's been flipped up onto the y-axis instead of the x-axis, but it's too much, right? This curve in black covers a greater region than my curve in purple, and the trick is that I am only allowed to use y coordinates where the smallest y can be is minus pi on 2, and the largest y can be is positive pi on 2. Ah, much better. So with that condition, now those two different curves are exactly the same. Well, hey, if I've got two different equations which give me the very same curve, I should be able to do implicit differentiation on either one of them and get the very same answer. One of these curves looks much easier to do derivative work on than the other, right? I got into this mess because I don't know how to do the derivative of the arcsine function. But I can absolutely take a derivative of sine of y equals x. That's actually pretty simple, right? I've been doing derivatives of trig functions for a whole week now, and I'm feeling really good at it. So let's take an implicit derivative. I'm going to throw my differential operator on there. So I know that the derivative, d on dx, applied to sine of y has to equal d on dx applied to x. Well, what's a dx on a dx? It's a 1. That is a bit glib. Power rule. What's the derivative of x to the first? It's 1. Okay. On the left-hand side, again, I have this situation where I'm taking the derivative of a function in y, and I am using the differential operator d on dx. I'm taking derivative in the x variable. That means I'll get the derivative of that function, which is the cosine of y, but I also need to multiply by my dy on dx. dy on dx is the conversion rate. That's what lets me change between a tiny change in x to a tiny change in y. So the equation that I get here, cosine of y, dy on dx equals 1. Okay, well, I can divide that. It says that my slope, dy on dx, is equal to 1 divided by the cosine of y. Now, the whole business with this region here, y must be between negative 2, pi on 2 and pi on 2, tells me that my cosine of y is positive. So I can say that cosine of y is equal to, well, cosine squared of y would be 1 minus sine squared of y. So a single cosine of y should be a square root of that stuff, right? Now, I need to know that the cosine function is positive so that I can use, so I know it is in fact the square root of that business and not minus the square root of that business. So I see cosine of y is equal to square root of 1 minus sine squared of y. I know what sine of y is. Sine of y is x. That's what got me into this mess. Sine of y is x. Here it is at the top of the page. So this cosine of y is really the square root of 1 minus x squared. That's going to go in here. Tells me that my derivative, dy on dx, is 1 divided by the square root of 1 minus x squared. And that gives me my derivative rule for the arcsine function. So we can do the very same thing for the other inverse trig functions. So for example, if I had y equals tan inverse of x, then tangent of y equals x, which means that dy on dx times secant squared of y equals 1, skipping some steps. And if I rearrange and do my substitution trick again, it tells me that the derivative of the arctangent function is 1 divided by 1 plus x squared. It can be done. We can calculate these new derivatives thanks to implicit differentiation.